So let's take a closer look at quantum compiling. So there's several aspects to quantum compiling. One aspect is what we call qubit allocation. So with qubit allocation, we know that we have logical qubits, or the abstract qubits that are associated with the circuit that we want to compute. But in reality, our hardware may have some constraints. So for example, on the top left diagram, we have a topology diagram in the purple. The purple graph shows a connectivity diagram that shows how different qubits for a particular platform may be connected. So given this hardware constraint, we may have to translate our abstract circuit to account for these connectivity constraints, and thereby introduce swapping operations that are shown in the right-hand circuit at the top. Another related problem is gate synthesis. How do we implement our logical gates in our abstract computation and map them onto the native gates available on our hardware? So this is usually a fairly straightforward process because the mapping is known a priori. Once we've performed our gate synthesis, we want to optimize the gate sequence. So for example, in this simple circuit we have in the middle, circuit that shows the X gate and C naught gate, we can swap the order of the two gates, and thereby after this swapping, there may be some opportunities to cancel the X gate with sequences that are subsequent in the computation. Or we may see that we have some operations that commute, and therefore they can be executed in parallel. And then finally, we may want to have very precise control of the pulse level control of our gates. So this would be at the very lowest level of our compilation process. So when we move from compiling for a single QPU to multi-QPU in a distributed quantum computation, we have a few additional concerns. We have to consider how we map our quantum circuit or partition it across multiple QPUs. How do we cut our circuit? How do we handle remote gate operations where the gate, the qubits associated with the gate cross a QPU boundary? And one helpful analogy that we can think about is for all of these compiling problems, it is broadly or roughly analogous to in a classical processor compiling a high-level language into native machine instructions, because we have a lot of the same processes. We have to map abstract statements to native machine instructions. We have to optimize the machine instruction sequence. So this is kind of a pretty good analogy that you can take. So as we mentioned, for DQC, we have to worry about crossing QPU boundaries. And so on the diagram in the middle to the left, we show a qubit moving across the QPU boundary. And how can we implement this? So one way to do this is that we can essentially develop or actually leverage quantum teleportation, which is a well-known process in quantum networking for transmitting quantum information. So quantum teleportation uses essentially uses a shared entangled pair, which we'll call an E-bit. And it leverages this in such a way that one of the qubits in the E-bit is shared with QPU1. The other is shared with QPU2. We have some extra operations and measurements. We have some classical communication. And through this process, we can transmit our state psi from the input to the output, where the output is on the second QPU. And in this case, the resources we required was one E-bit for operations, 2 measurements, 2 classical channels across the boundary. Another way we can do this when we have a 2-qubit gate that straddles the QPU boundary is called gate teleportation. So it's similar in a lot of ways. We have the boundary, we have a shared E-bit, 1 qubit from that E-bit is shared with QPU1. the other shared with QPU2, and we do some extra operations measurements, and we can reconstruct the input-output relationship of our original 2-bit gate, except now that we're operating across 2 QPUs. So in this case, we had the resources that we required was 1 EBIT, 6 operations, 2 measurements. We actually did not require any classical channels across the QPU boundary. So we can actually take these two remote operation strategies and bring them together for our overall goal of quantum circuit partitioning. So in the top circuit, which we call, it's been partitioned in one way, which we call partition 1. And in this way, we've leveraged only gate teleportation. Our partitioning has cut through the circuit along these 4 CNOT gates. So we have 2 qubit gates that are straddling the boundary. So we're leveraging gate teleportation. We use 4 EBITs. But if we can use both gate teleportation and qubit teleportation, then we can cut the circuit another way. So in the second partitioning scheme, we've cut along 2 of the CNOT gates across the control qubit, but then we've cut across the circuit between our T gate and our other the subsequent CNOT gate. And in this case, with this cutting, we only have 3 EBITs required. So overall, you can think about the partitioning process as an optimization problem where we want to balance the resources across QPUs in some appropriate way. We want to minimize the resource cost of the graph cuts. Now, balancing the resources, if the QPUs are roughly have the same capability, that would translate into roughly the same computation, sort of load balanced across the QPUs. Or if one QPU has more computational resources available, then you would balance those resources accordingly to the capability of the QPU.